New pictures obtained by the James Webb Space Telescope have stunned researchers. As opposed to growing our cognizance of the universe, these pictures revealed a disturbing reality. Our ongoing comprehension is insufficient to grasp the possibility of the universe in its starting stages, where the hypothesis of the universe's origin appears at its limits. This constrains us to contemplate new hypotheses about its beginning stage. The question arises as to how the universe was formed thoroughly, and why this new revelation challenges even the most experienced space specialists to sort out more about the Big Bang and the dynamic nuances of the discovery. We ought to review the possibility of the Big Bang itself, rather than predominant thinking. The Big Bang was not an impact in earlier space. Rather, it was space itself that began around 13.8 billion years ago, alongside matter and time, from a unique quirk in actual science and cosmology. A natural description where gravity is so unprecedented that the curvature of space-time becomes endless. Today, following billions of years since the beginning of the universe, we see that our infinite home is part of a significant communication for experts. This addresses a critical part of the universe, since its very existence. Its evidently ceaseless development is necessary to grasp the universe. It isn't wandering into earlier space. Rather, space itself is constantly growing in size. According to conventional hypotheses, the first stars began to shine somewhere between 200 and 300 million years after the Big Bang, marking the end of the supposed Dark Age. This was when the first glowing celestial objects bunched together to form mature galaxies. However, how quickly these galaxies developed remains a baffling question. A huge piece of data arose through the first pictures captured by the James Webb Space Telescope in July 2022. Subject matter experts revealed that the telescope had identified various galaxies, some of which had already existed around 300 million years after the development of the universe. However, contrasted with the vast structures that formed billions of years later, these early cosmic systems were significantly more modest and less massive. This fits perfectly with the scientific model accepted by experts. The density of matter in the early universe was simply not sufficient to lead to galaxies the size of those observed today. This began with the discovery of 6 amazing redshifted bright spots from James Webb, which ended up triggering one of the most critical cosmic crises of recent times. Despite the fact that these newly discovered galaxies are comparable in age to recently recorded galaxies, they are close to being as immense as our own Milky Way galaxy. This has created a fascinating mystery in cosmic cosmology. After examining a series of pictures caught by the near-infrared camera, experts identified the recently mentioned light sources using redshift. Analysts confirmed that the light from these objects took more than 1 billion years to reach our eyes on Earth. Thus, we are dealing with structures that had already existed somewhere between 570 and 700 million years after the confirmed Big Bang. By looking at the characteristics of these designs, it was concluded that the Webb telescope had captured 6 early systems in the image. Incredibly, these systems were so colossal that they challenged conventional assumptions of cosmology. Rather than finding the usual dwarf galaxies, structures were identified that were nearly as large as our own Milky Way galaxy, despite having formed early in the cosmic timeline. If we continue to examine the data gathered by the James Webb Space Telescope, this gravitationally bound assortment of stars was already more than 10 billion times the mass of the Sun at that time. With one possibly incredible 10 billion solar mass imprint, whether this chance is viewed as the secret isn't completely settled. Even in this situation, there would be essentially more astronomical mass in the early universe than recently anticipated. Introducing a riddle. The recognized objects go against practically all traditional cosmological hypotheses. Even if by some stroke of good luck one of these universes ends up to be real, it would challenge our past suspicions to make sense of the presence of these designs. Besides, the thickness of matter in the early universe would need to be on different occasions more prominent than recently acknowledged to make sense of this peculiarity. Another comparably bizarre explanation depends on the possibility that these galaxies formed in a way that is still totally dark to us. These revelations and the discussions they are heading to encompass regarding the Big Bang have led more experts to remove themselves from this hypothesis. Many scientists with alternative perspectives are astounded, and their points of view are frequently heard in scientific journals. Even those who express doubts about existing hypotheses are often marked as outlandish. However, it is clear that even experts who still defend the Big Bang hypothesis are consistently faced with inquiries without unambiguous responses. These inquiry questions include explicit issues, for example, why and how, 13.8 billion years ago, something literally rose up out of nothing. Could something really start from nothing? Or was there some triggering event? Or was it all a mishap? Steven Weinberg pointed out that the concept of time as we know it began with the Big Bang. Consequently, this process could never have been set off by something else or by an external cause. A similar ambiguous question relates to the consistency of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find comparable densities and distributions of galaxies, nebulae, and radiation. All moderate specialists explain this peculiarity by the theory of infinite expansion. However, various experts expand this assumption further with a theory of tumultuous expansion. According to this thought, expansion has only halted in certain regions, like bubbles, and continues incomprehensibly elsewhere. This suggests that various universes could form in these bubbles, each with its own unique physical laws. Within this model, a crucial question emerges. What if the universe doesn't represent the total whole? More creatively, consider the possibility that another universe existed before our own. In this case, the Big Bang would become a part of a larger cycle. According to this perspective, our universe is part of a bigger complex structure. Within this model, the chance of a timeless pattern of breakdown and resurrection of the universe is advanced. However, this isn't the only perspective presented in the realm of cosmology. Apart from the theory of how things came to be, in 1955, for instance, an article appeared in NASA's Big Times arguing that there may have never been a Big Bang since the universe has existed for an endless period. In this view, the development of the universe would be non-existent, and the constant improvement of matter could give the impression of consistent development. Furthermore, another captivating and questionable speculation comes from the realm of quantum physics and string theory. Some tests have suggested that our universe and everything in it may be a projection or a higher dimensional reproduction. While this could appear as the plot of a capricious science fiction film, it could be connected with the Kardashev scale, which assesses the level of advancement of a civilization according to its capacity to harness energy. If there were a Type 3 civilization capable of completely utilizing the energy of a whole galaxy, it could have created an ideal recreation. However, grasping reality in such a situation is a profoundly complicated matter. Examining the depths of cosmology and the beginnings of our universe leads us into a domain of significant mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited conversations about the actual texture of our reality, testing established theories and provoking specialists to reconsider key aspects of cosmological understanding. At the center of this inquiry lies the hypothesis of the universe's starting point, a foundation of modern cosmology. According to this hypothesis, approximately 13.8 billion years ago, the universe arose out of an inconceivably thick and hot state, expanding rapidly and leading to space, time, and matter as we know it today. This immense event was not just a blast within previous space, but encompassed the absolute beginning of space itself. The idea of a singularity, where attractive energy forces are so extreme that space-time curvature becomes infinite, supports our understanding of this early stage. Yet, the discovery of early galaxies by the James Webb Telescope difficulties raise our suppositions about how quickly structures framed in the universe's earliest stages, these cosmic systems recognized inside 200 or 300 million long stretches of the Big Bang, show up shockingly full-grown and large, looked at in current cosmological models. One of the key inquiries raised by these disclosures is the concept of grandiose expansion. As indicated by the predominant hypothesis, expansion happened within parts of a second after the enormous detonation, making the universe grow decisively. This quick development would make sense of the consistency of the inestimable microwave background radiation noticed across the universe today. However, current discoveries suggest complexities in the early universe's advancement that may require changes to inflationary models. The advancement of universes like those seen by the James Webb Telescope forces cosmologists to reevaluate the conditions and cycles that governed the universe's initial history. These cosmic systems, now significant in size and mass, so not long after the Big Bang, suggest a density of matter that surpasses past estimates. The secret broadens when considering how such gigantic designs could shape and develop in such a somewhat short, enormous time. Besides, the revelation of these early universes brings up interesting issues about the nature of dark matter and dark energy, two slippery components that constitute the majority of the universe's mass and energy content. While dark matter is accepted to provide the gravitational structure fundamental for cosmic system arrangement, the distribution and properties of dark matter in the early universe remain unsure. Aligned with these astrophysical secrets, hypothetical physicists are investigating elective cosmological models that challenge the regular Big Bang perspective. Some hypotheses propose that our universe is only one among numerous in a tremendous multiverse, each with its own unique actual regulations and constants. These thoughts, rising out of advancements in string hypothesis and quantum cosmology, propose a more complicated and interconnected universe than recently imagined. One thought gaining footing is eternal inflation, where universes consistently rise out of a larger blowing up space. This hypothesis suggests that our universe could be simply one bubble among innumerable others, each with its own specific properties. The challenge lies in finding observational proof to support such theoretical thoughts as they push the limits of exact approval. Another provocative hypothesis suggests that our universe exists within a simulated reality, likened to a computer-generated recreation. This idea draws parallels to advancements in artificial intelligence and computational science, where recreations can reproduce complex frameworks with astounding loyalty. If true, our view of reality as an unmistakable actual universe could be fundamentally changed, raising huge philosophical and scientific inquiries about the nature of existence. Moreover, advances in observational space science continue to uncover the universe's vastness and intricacy. Telescopes like the James Webb Space Telescope, with their striking responsiveness and resolution, promise to disclose even more mysteries of the universe. Future observations might reveal insight into the earliest moments of the universe, providing clues to its ultimate destiny and the fundamental principles governing its development. Beyond observational cosmology, particle physicists are examining the key particles and forces that shape the universe. The quest to unify gravity with the other three crucial forces, electromagnetism, strong nuclear force, and weak nuclear force, remains a central objective of theoretical physics. Models such as quantum gravity and string theory offer possible frameworks for understanding these fundamental connections at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a subject of intense discussion. Quantum theories suggest that time might be new or even slippery at the fundamental level. Understanding the concept of time within the context of cosmological models could reshape our comprehension of the universe's beginnings and development. Moreover, the quest for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets circling stars beyond our solar system, has expanded our understanding of planetary variety and the potential for habitable conditions elsewhere in the universe. Future missions, for example, the James Webb Space Telescope's investigation of exoplanet environments, might provide proof of biosignatures indicative of life beyond Earth. Notwithstanding these scientific attempts, cultural and philosophical reflections on the universe enhance our understanding of our place in it. Inquiries about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration drive exploration and discussion across disciplines. As we stand on the verge of a new era in space science and cosmology, energized by mechanical progressions and theoretical breakthroughs, we are reminded of the significant interconnectedness of everything, from the smallest subatomic particles to the tremendous cosmic structures spreading over billions of light years. The universe reveals its mysteries to those willing to explore and inquire. In conclusion, the investigation of the universe and its origins is a journey that transcends disciplinary limits and challenges our fundamental assumptions about reality. The disclosures made by instruments like the James Webb Space Telescope offer tempting glimpses into the early universe and pose new inquiries about its development and advancement. As we continue to unravel the mysteries of dark matter, dark energy, and cosmic inflation, we draw closer to a more complete understanding of the universe and our place within it. Through collaboration among astronomers, physicists, scholars, and technologists, we embark on a grand journey to decode the vast code, an endeavor that promises to rethink our understanding of existence itself. Whether investigating the depths of black holes, charting the paths of distant galaxies, or examining the concept of reality, every discovery brings us closer to unwinding the complex tapestry of the universe. As we venture further into the cosmos, guided by curiosity and driven by a longing to grasp the universe's enormity and intricacy, we are reminded of Carl Sagan's words, "Somewhere, something incredible is waiting to be known." This sentiment encapsulates the essence of scientific exploration, a continuous journey of discovery, wonder, and enlightenment that continues to inspire generations of researchers and thinkers alike. In the words of Albert Einstein, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science." As we confront the mysteries of the universe, we are invited to embrace uncertainty, challenge our assumptions, and seek new perspectives that expand our understanding of both the universe and ourselves. Consequently, the exploration of the universe is not simply a scientific endeavor, but a profound human journey for knowledge and significance. It is a voyage that transcends the boundaries of reality, inviting us to contemplate our position in the magnificent tapestry of existence.